Alright, so here in this video we have a stunt car that is going off horizontally. And it says here the car leaves and falls freely to point A here in the diagram in a time of 0.5 seconds. And it says to point B in a time of 1 second. Okay, and it wants to do A, B, C, D, and E. Alright, pause, read, keep up. Part A wants you to find the car's initial velocity V. So here in the diagram, here's the car and it's initially moving in the horizontal direction. It's going to go off the cliff. So here's V. Okay, so we need to find what that V value is. Now, the quickest way to find V based on the information here. So if you look at the diagram here, so it's going to fall some vertical distance D, which is not given to us. However, in the horizontal axis here, the horizontal distance is given because here in the diagram it says distance from the base of the cliff. This is 8 meters and that's 16 meters. So after 0.5 second, it has traveled horizontally 8 meters. After 1 second, it has traveled horizontally 16 meters. So we can use one of these points A or B to find V. Okay, so I'm just going to set up my horizontal information here because I know my horizontal distance or displacement in this case. Okay, and the question is asking for V, which happens to be in the horizontal direction to start with. So this is an well, not easy, but straightforward problem. Okay, so I'm just going to set up my displacement function. I want to remind you that in two-dimensional motion, AX is assumed to be 0 unless otherwise stated. Okay, so I'm just going to go ahead and cross out the AX here because AX is 0, so 0 times 1/2 times t squared is just 0. So really the function is simply just delta x is equal to VIX times t. Okay, well, this particular part asks you to find the car's initial velocity V. Okay, so once again, in the diagram, it's just called V, but really you have to, look at it. It's really just VIX because it's pointing straight in the X direction. Okay, so in my work, I have VIX, which is the same as the V in the diagram. Well, here, this is pretty straightforward. I'm just going to choose point A, its information. So after 0.5 second, the car has traveled or a distance of 8 meters in the horizontal direction. So for delta x, I'm just going to put in 8 meters, and then for the time, I'm just going to put in 0.5 seconds because it's given in the wording here. It said that it fell from start to point A in a time of 0.5 seconds. So if we clarify that up, 8 divided by 0.5, which is 16. And here I included the plus sign because in this diagram, the car is initially moving in the positive direction or to the right. And because it asks for initial velocity, I will just include the direction there for you. Okay, so that's part A. Now, part B says determine the magnitude of the horizontal component of the velocity at point A. Well, this one is kind of just to troll you. So here, I just found that VIX, or V here in this problem, horizontally is 16 meters per second, right? Part B asks you to find the magnitude of the horizontal component at point A, and that's just to kind of mess with you. Keep in mind for two-dimensional motion, right? Because AX is equal to 0, the car or object or particle does not accelerate horizontally. It just accelerates downward due to gravity. Okay, so therefore, because AX is 0, your V must stay constant, right? The object is not accelerating in that direction. So here I made a statement for you, which is important. Vx stays constant. So therefore, we already found initially that the car is moving in the horizontal direction at a rate of 16 meters per second. Well, the answer for part B needs to be the same because Vx cannot change. It must remain constant for the whole entire duration. Okay, so that's that. Part C. C wants you to find the magnitude of the vertical velocity of the car at point A. So here we have to find the vertical component. Well, to find the vertical component, I'm just going to set up my Vf is equal to At plus Vi. But you notice here in my work, I just put Vf with the subscript y because the question asks for the vertical velocity. So you can apply your kinematics equation. You just have to make sure that you're using information in the y direction and in the x direction separately. Do not mix up these values. Otherwise, you are going to goof on your calculation, okay? So what is Vfy? I don't know. That's what I'm trying to find. What is A? A is just acceleration due to gravity, which just got replaced with G. T is 0.5 because it says point A. Okay, and what is Vi? Well, the car's initially moving horizontally, so there is no Vi component, right? The arrow is perfectly straight, flat. Right? There's no up and down, so therefore VIY is 0. So to clean it up, G is simply negative 9.8, and then the time interval here at point A is just 0.5 seconds. So therefore, the vertical component is negative 4.9 meters per second. However, part C says the word magnitude. So if it does magnitude, you just have to make sure you get the absolute value. Okay. Now, Visually in the diagram, here's point A, here's Vx, which is 16 meters per second. I just found this vertical component, and it points down because the object is moving right and down. So therefore, this value here, Vfy, is negative 4.9 meters per second. But once again, the answer for part C is just 4.9 because it wants the magnitude. So in my work, I just did the absolute value for you there. Okay, let's do D and E. All right, part D wants you to find the instantaneous velocity at point B. This one's a little harder. Okay, so as the object falls, its Vx remains constant, but its Vy keeps growing and growing and growing because it accelerates downward. So here's my V. Your V should be, a tangent line to the path of the motion here. So I just drew that arrow there for you. That is the V that I'm trying to find. However, to find that diagonal, I need to have a couple of pieces of information. I need a Vx and a Vy. Well, Vx here is super easy because we already found it, right? It's 16 and it has to remain the same for the whole entire problem. Vy, I don't know. So at point B, I just know that it's moving down and it's getting faster and faster in the y direction, but I don't know what that value is, so I'm just going to call it Vy. So really the only thing I need to do is find Vy, and I can then do Pythagorean theorem because this is the right triangle, okay? So let's find Vy real quick, right? To find Vy, I can just set up Vfy is equal to At plus Viy. Again, this is just your final velocity is equal to acceleration times time plus Vi, right? But the subscripts here is just to help you organize your information. Well, what is your Vy? Viy. Viy 0 because the car is initially moving horizontally. So therefore, G is negative 9.8. And then T here is 1 second because I'm at point B. And the problem is just that it takes 1 second to get to point B, right? So therefore, negative 9.8 times 1 is just negative 9.8. So therefore, I just found the vertical component at point B to be negative 9.8 meters per second. And it's pointing down because the object, once again, is moving to the right and at the same time falling downward. So it traces out this nice, curvature. Okay. Well, what do we do with that? As I stated earlier, once you have this, you have a right triangle. So to find the hypotenuse, you would just do Pythagorean theorem. So V of t is just V, right? And then you would do Vx squared plus Vy squared because this is your, your adjacent and this is your opposite. So therefore, we plug it in. Vx is just 16 because we already found that in part A. We're going to square that. Vy, we just found, that's negative 9.8 at 1 second. And we're going to square that. And if you do all that correctly on the right side, it reduces down to 352.04. But this is V squared. So to get V by itself, we need to square root both sides. So the square root of 352.04 will give you roughly 18.76 meters per second. Yeah. So that's that. Okay. However, keep in mind that it says instantaneous velocity. What I just found here is just the speed. Okay. When you take the square root of a number, you get a positive or a negative. However, this is a two-dimensional problem, so you can't just stop here. You have to give a direction, and your direction must be in some form of angle. Okay. So in my work, I highlighted that theta for you. Theta here must be touching the horizontal axis as the reference point. So that's why I put that theta and it touches Vx because that's the reference point that's accepted. Okay. So to find theta, all we have to do is set up tangent of theta is equal to Vy over Vx because tangent is opposite over adjacent. And opposite in this case would be Vy. My adjacent is Vx. And to find theta, we just do inverse tan. And then Vy and Vx we already calculated, right? Vy at 1 second is negative 9.8. Vx at any time is 16 because it doesn't change. So once you plug that in your calculator, hopefully in degree mode, if you're in degree mode in your on your graphing calculator, you should get negative 31.5 degrees. So the proper way to express my answer here is 18.76 meters per second, which is the speed. And then I need to give the direction, which has to be in the form of an angle. So that would be 31.5 degrees southeast because this arrow is pointing down, which is south, and then right, which is east. Okay, so that's part D. Part E wants you to find the magnitude of the vertical displacement, dy. So here in this diagram, dy is the distance in the y direction from point A to point B. This one's not too bad. So I think the easiest way to do this one is just set up your displacement function. Yeah, just make sure you use the Vy or the initial velocity at the right time. So here, Viy, I'm actually going to plug in negative 4.9. Oh, I should say meters per second, by the way. Excuse me. Okay. By the way, so if you're watching this, this should say negative 4.9 meters per second, not second. I goof on the unit there, so let me just fix that real quick. Okay. Okay. Oh. All right, let's go back to here. All right, so let me do that. So this should be negative 4.9 meters per second because I already calculated that in the previous slide. So after 0.5 seconds, it's moving down at a rate of negative 4.9 meters per second. The time here is just 0.5 because, well, point A already took a half a second. And then from a half a second to a whole second is just a half a second, right? So 0.5 to 1 is just 0.5 difference. That's why the time here is 0.05, okay? And then G is just negative 9.8, and then here time once again is just 0.5 seconds, and we're gonna square that. And if you clean all this up on your calculator, you should get the first term would be negative 2.45, and then want to add it, but then this negative 9.8 times a half times 0.5 square will give you negative 1.225, and then if you simplify that, you have two negative values here, which will make a bigger negative value, which is negative 3.675 if you add it on your calculator. Okay, so that is your, well, almost answer there. But you notice here in the problem it says magnitude, so I would just give you the absolute value, right? So it's just looking for the distance down. So the distance down here, which is 3.675 meters, because distance is a scalar, or the word magnitude imply that you just need to give the value itself. Okay, that's the quickest way I think to do it. You just have to be careful that you don't plug in VIY 0, right? Because the problem didn't start at 0 second; it actually started at 0.5. So at 0.5 second, it's already moving downwards. So make sure your VIY is correct, otherwise you'll goof. Okay. The other way to do it is to just find how far did it fall during the first half a second, and then how far did it fall during the first second, and just subtract the difference, or just subtract the two values, find the difference. Okay. So here I'm just going to do slightly different. I'm going to find out how much did it fall from start to just point A in the vertical direction, so delta y. So here, if I do that, my VIY is going to be 0 because I'm starting at times equal to 0, right, where the car physically leaves the cliff here. So really it reduces down to just 1/2 GT squared. G is given as negative 9.8. Time here is 0.5 because from start to point A is 0.5 seconds. So if you clean that up in your calculator, you get negative 1.225 meters. I'm going to do the same strategy. I'm going to start from, again, where the car leaves and then go down to 1 second. So if I start from the very, very beginning, my VIY is 0 because it was leaving the cliff in the horizontal direction. So there's no VI component. On that same work here, except the time here is just 1 second. So if you clean this up, you'll get negative 4.9. And then once again, you're not done here yet. Yeah? You just found the two distance from 0 to A and then from 0 to B. So you still need to take these two values and subtract to find the distance. So how far did it fall down to point B, 4.9? Minus how far did it fall from start to point A, 1.225. So how far is it from A to B, which is just 3.675. As you can see, it's the same answer. Okay. Now, if you know your ratio, you can do this. Okay. I like this strategy. It's pretty quick. So here, from 0 to A, which is a half a second, I'm just going to reference that as D. That's my baseline. But what I do know is that from 0 to 1 second is twice the time, right? So from 0 to 0.5 is 0.5. And then from 0 to 1 is 2 times 0.5, right? Because 2 times 0.5 is 1. But anytime you double the time, you quadruple your displacement in that direction, assuming VI is 0 in that direction. And for this problem, VI is 0, so I can use this strategy. So for the first half a second, it fell a distance D. For the first second, it fell a distance of 4D. So therefore, how far did it fall from 0.5 to 1? That would just be 3D. And what is your D in this case? Your D would just be your baseline from 0 to A, which is 1.225 that I'm circling with my cursor here. So if you take that value and you times it by 3, you'll get the same answer. Okay. All right. I hope that helps. Stay nerdy. Don't be wired.